Hello students and welcome to the video on extrinsic semiconductors. So now I hope you know the basics of what is the band theory, how are solids classified according to band theory, and we know that semiconductors is one type of classification in the band theory where the energy gap between the valence and conduction band is very less that it can be overcome by applying some external conditions. So that is what is semiconductors. Now, we already learned what is a pure semiconductor. The pure semiconductor is also known as intrinsic semiconductor, and they are basically the semiconductor or the elements in their purest form. So then what is extrinsic semiconductor? That is the next type of semiconductor that you're going to study. So basically we have only two types of semiconductors. One is the intrinsic, which is a pure semiconductor, and then we have the extrinsic semiconductor. So now intrinsic semiconductor, what are the examples? The examples was silicon, germanium, etc. So now we are going to learn what is extrinsic semiconductor. And to learn what is an extrinsic semiconductor, we should know what is doping, what is an N-type semiconductor, and what is a P-type semiconductor. Actually, if you know what is doping and you understand the concept, then you can divide semiconductors, basically extrinsic semiconductors, into two types. One is the N-type and the other one will be the P-type. Okay, I hope you all have seen this image before. It is nothing but the periodic table, which is a representation of classifying elements according to their valence number and according to its characteristics. So now to the left of the figure, you have the metals, and to the right side, you have the non-metals, and here in between group 14, you have the semiconductors. So these semiconductors are just pure form of the element or the intrinsic semiconductor. That means they have only the element in their purest form and no other impurity is found in them. But what happens is, if you just use the semiconductor just as it is, you will not get all the properties that you require that can be used to make semiconductor devices which you have been using in your gadgets and all. So for that, what scientists do is they will add some form of impurity. Impurity is nothing but some other element. Okay, so they'll be adding it to the semiconductor material, and then it will be mixed in a particular way. There are different forms of this process, and this process of adding some element or some impurity, as we call it, to the semiconductor pure material is known as doping. So what is doping? Doping is adding impurities, and the impurity which is added, we call it dopant. So I hope you understood what it is. So if you look closer to the periodic table, we have now selected the group 13, 14 and 15 elements. The 14 group is the semiconductor. Now to add impurities, the ideal elements used are the elements of the groups which is near to the group 14. That is either group 13 elements which contain boron, aluminium, gallium, indium, etc. And then or group 15 which contains nitrogen, phosphorus, arsenic, antimony and bismuth. So these are the dopants that we will be using to create impurity and improve the performance of the semiconductor so that it can be made into devices of our choice. So now this adding of impurities can classify semiconductors into two types, which we had already seen before. One is the N-type and one is the P-type. Now I'll tell you which one is N-type and why is it called so, and likewise why is it called P-type. So to understand the doping process, we need to know, or we need to have an idea about the number of valence electrons present in each of the element. So now group 14, silicon. It has how many electrons? You can count 1, 2, 3, 4. So 4 electrons. Now we are considering phosphorus. Don't mind the B, it is a mistake. So phosphorus has how many electrons? 1, 2, 3, 4, 5. So if this silicon and phosphorus are joined together, see, joining together means if one phosphorus is surrounded by many silicons, it can share the electrons. That is what I meant by joining. We cannot have any other process, only covalent bonding is allowed here, that is sharing of electrons. Now, in that sharing process, 8 electrons are seen around the phosphorus, but there is a 9th electron here because there is 5 electrons of the phosphorus and each of the silicon around it is providing 1 electron. So 5 plus 4 becomes 9. That means 1 electron is extra. As you know, we need only 8 electrons in the valence shell. So this 1 electron that is extra will be the free electron. This free electron, when this phosphorus is added to a very big sheet of silicon material, there will be many sites like this where this phosphorus will be surrounded by silicon. Then there will be a phosphorus here, a phosphorus here, a phosphorus here, a phosphorus here. They all will be surrounded by silicon again, and this goes on. So there will be many phosphorus. That means as many phosphorus atoms are there, those many free electrons are present. So you think what would be the condition? There will be free electrons present in the entire material ready to move. And this extra electron becomes the charge carrier here, and because it is a negative charge carrier, this is known as negative type or n-type semiconductor. It has one more name, which is pentavalent, because the dopant used here is phosphorus, which has 5 electrons. 5 means penta, so pentavalent. So I hope you understood the idea. So now, if we uh, connect this semiconductor material of n-type to a circuit where the positive is here and the negative is here, see, the electron is always moving to the positive side, and this from the negative side it starts going and then it moves like this. In between you can see some charge carriers moving to this side. That means they are charge carriers of the opposite charge, that is positive charge, and we call them as holes. Okay, earlier we discussed about the group 15 elements. Now suppose we are adding group 13 elements, for example boron, to the silicon layer or material. So what happens? This boron is placed in the middle and silicon is surrounding it. Silicon has 4 valence electrons, but boron has only 3 and 1 is empty. When you place it here, again in the valence, instead of getting valence fully valent by getting 8 electrons, it has only 7 electrons. This 3 plus this 4, so 7, and there is a gap here. This gap or vacant area, we call it as a hole. Because it is an absence of the electron, we consider this hole to be a positive charge. And now when we consider the entire material and there are many boron atoms added to the material, then those many number of holes are generated and they are simply positive charge carriers. Because of the positive charge carriers, this type is known as positive type, or in short form p-type. And because the dopant added has only 3 valence electrons, this type is called as trivalent. We look at the circuit, we can understand that if a p-type material is given and the positive side is here and the negative is here, electrons as they move from here to here, we believe that holes are moving in this direction, that is from positive. When this is positive, it gives a push, so it moves to this side. The other side moving charge carriers are nothing but the free electrons, which will be in minority. These minority charge carriers are due to the temperature difference and all, which is due to thermal conditions and all, but this majority are simply due to the doping. So in this image, the difference between the p-type and n-type is shown. See the p-type we have, which is p-type. This is p-type where the hole is present, and n-type there is an extra electron present. It is represented like this because there is an electron going out. So it can be given to somebody. It is known as donor impurity. Now here there is a vacancy where somebody can come inside. So it is known as acceptor impurity. So keep these two terms in mind, donor and acceptor. So I hope the concept of doping, the concept of N and P type semiconductors and extrinsic semiconductor is clear to you. If you have any doubts, kindly leave it in the comment section and suggest the topics that you require as video. Thank you so much for listening.